Welcome to this video on the Fourier transform of basic signals, part of the Engineering Mastery series. We begin with section 01, which will provide an introduction to the topic. The purpose of this study is to understand fundamental transforms, which are essential for analyzing complex waveforms. These basic signals serve as the building blocks, or DNA, for sophisticated communication systems. Moving on to section 02, we will explore the impulse signal. The unit impulse, or Dirac delta function, is an ideal spike signal. It is infinite height, zero width, and a unit area, as shown by the formula in the diagram. The Fourier transform of the impulse signal is a constant value of 1. This flat spectrum means the impulse contains all possible frequency components equally, making it perfect for testing a system's instant response. A key interpretation is that the impulse provides 100% spectral coverage. It effectively excites every single frequency in the universe with equal intensity. When we consider a shifted impulse, a delay in the time domain corresponds to a phase rotation in the frequency domain, as shown in the transform equation. Next, we move into section 03 to analyze trigonometric signals. The cosine waveform represents pure harmonics. This signal is a single, steady frequency, often called the fundamental pure tone in acoustics and RF engineering. The Fourier transform of the cosine function results in two impulses in the frequency domain. These spikes are relocated at positive and negative frequency peaks, and the area of each impulse is pi. These spectral spikes illustrate that a pure sinusoid's energy exists only at the specific frequencies plus or minus omega naught. The sine waveform is similar to the cosine, but it is shifted by 90 degrees. This phase difference introduces the imaginary unit j in the frequency domain representation. The Fourier transform of the sine function yields imaginary spikes with odd symmetry. The result is a 90-degree phase shift due to the time shift property relative to the cosine. The key insight is that continuous time waves, like sines and cosines, simplify to discrete points in frequency. These are the pure tones we observe in the spectral domain. We now begin section 04, focusing on the rectangular signal. The rectangular function, also known as the pulse, is a finite duration signal defined by these equations. It has an amplitude of 1 for a time duration t, centered at the origin, and 0 elsewhere. The pulse is characterized by a constant amplitude of 1 for the duration t, immediate transitions at its start and end, and is centered at the origin t equals 0. The rectangular pulse is strictly time-limited and has finite energy. This limitation has profound consequences, leading to an infinitely wide spectrum in the frequency domain. Next, in section 05, we will derive the Fourier transform of the rectangular signal. Applying the Fourier integral over the pulse's finite duration yields the following integral expression. Solving this integration results in the famous sinc function. The Fourier transform result is the sinc function, which represents the frequency domain. This is an oscillating decay, showing how energy spreads across the frequency spectrum. The sinc function has a peak value of 1 at x equals 0. It features oscillation, alternating between positive and negative peaks, and a characteristic decay where the amplitude decreases as 1/x. The spectrum consists of a main lobe, which contains the most energy, and surrounding side lobes, which represent spectral leakage. The width of the spectrum is inversely proportional to the time duration. The sinc function exhibits symmetry. Since the rectangular function is a real and even signal in the time domain, its Fourier transform is also real and even in the frequency domain. The sinc function crosses 0 at integer multiples of pi, known as the nodes, excluding the origin itself. This is where the energy is 0 in the spectrum. Finally, we transition into section 06 to discuss the key relationship between the time and frequency domains. This inverse relationship, often called the uncertainty principle, dictates that you cannot compress a signal in time without expanding it in frequency. This principle is fundamental to signal bandwidth analysis. A narrow pulse, characterized by a small t, represents a fast event in time. This compressed time requires a wide spectrum, or huge bandwidth, to represent the rapid change. Conversely, a wide pulse, with a large t, is a slow, lingering event. This expanded time corresponds to a narrow spectrum, requiring minimal bandwidth. Now in section 07, we focus on visualization insight to better understand the time-frequency relationship. From dual perspectives, a finite pulse in the time domain, which exists only for duration t, becomes an infinite, spread-out sinc function in the frequency domain, extending to infinity. This illustrates the inverse scaling trade-off. Compressing a signal in time means expanding it in frequency, and expanding it in time means compressing it in frequency. Section 08 presents a summary table of the key signal transformations we have discussed. This reference chart provides a comprehensive overview of the fundamental signals in the time domain and their corresponding transforms in the frequency domain, a key tool for analysis. Moving to Section 09, we will examine the real-world applications of the Fourier transform. In communications, the Fourier transform is used for pulse shaping in transmission, filtering noise in digital signal processing, and allocating bandwidth for systems like 5G and Wi-Fi. For electronics, it is critical for circuit analysis, helping us understand how filters handle rectangular pulse clock signals and pure tones. It is also used to analyze clock stability for jitter and pulse width in CPUs. In Section 10, we will gain an advanced insight into the practical interpretation of these concepts. In a spectral view, engineers can identify component frequencies, allowing them to isolate and remove unwanted signals and chaotic noise in real-world studies. When dealing with bandwidth, the main lobe's width in the sinc spectrum primarily defines the required bandwidth for the signal. A key design principle is the trade-off. Engineers must balance the need for high-speed pulses, which require wide bandwidth, against the need for efficient spectrum use, which uses slower pulses. System design requires balancing these Fourier properties. Finally, we reach Section 11 for our final understanding of the Fourier transform and its basic signals. Thank you for watching this video. We hope this has clarified the fundamental concepts of the Fourier transform for basic signals. The images used in this video are sourced from the links provided here.